All right, so Dirac Fermions interfaces. So thank you all for coming to my talk. I'm just finishing my first year as a PhD student, confirmation, yeah, I'm working in condensed matter physics, studying phenomena of solid state materials, which are relatively static collections of atoms. This is responsible. The theory is pretty responsible for a large amount of our electronics and technology sort of advances. So let's get into it. So I guess I get to give you a bit of a sense of a direction. I'm going to first introduce you to what Dirac systems are, and I'll show you some of the consequences of observing Dirac sort of behavior in particles, and especially in crystal sort of systems. I'll give you some examples of phenomena that arise from these sorts of systems, and then touch on a little bit of the work that I've been doing in graphene, which is a Dirac material. And what I want to do coming up in the next couple of years. So that's the rough outline for the talk. So yeah, I guess what is a Dirac fermion? So Dirac fermions are particles that behave according to Dirac's equation, formulated back in 1928. Dirac tried to derive basically the relativistic hydrogen Bohr atom energy levels. And this was in particular used to model spin half particles. And so the solutions come out as these objects called bispinors, where the complex components sort of describe the real space orientation of a magnetic moment or a magnetic dipole. You can model the relationship between the energy and momentum for Dirac particles. And in the massive case, you get something that's sort of parabolic, between a parabolic relationship between the energy and the momentum of these particles. However, you can also do the same for a massless case. And here you get Dirac fermions with distinctly linear dispersion. And it turns out this relationship has very distinct sort of results for the particles that result from them. So what sort of systems can we actually observe this Dirac behavior in? In materials, crystals, so arrangements of atoms over long scales, give rise to periodic potentials and quasi-particle behaviors. It's very common here to observe, it's very common in materials to observe parabolic dispersions for particles, like shown here for silicon, especially around the Fermi energy. Usually this curvature is sort of related to how responsive a particle is to an electric field or its mobility. It turns out that in some recent materials, however, that there are materials that exhibit linear sort of dispersion relationships. This is an example of the band structure of graphene. And you can see that at the K crystal momentum point, that the band touches in a very linear way at the Fermi energy. This is new and profound because the electrons in the crystal are behaving very similar to that of the massless relativistic Dirac fermions. Quasi-particles that are massless in that sort of way. So I guess what's special about these linear dispersions in Dirac materials? As I mentioned before, the solutions to the Dirac equation come in these mathematical objects called bispinors. And there are two sets of materials predominantly that are researched for the Dirac physics, graphene and topological insulators. So the Hamiltonian of both of these particles have Dirac quasi-particle sort of properties. Yeah, I guess the bispin actually has a really important significance. In graphene, the real spins are degenerate. However, the solutions to the Hamiltonian actually describe another sort of quantum spin object called a pseudospin. In topological insulators, however, it's actually the real spin that is described by these solutions. So yeah, I guess what's sort of important here is that the spin sort of property in each of these materials is sort of locked to the momentum direction in the same sort of in what you observe here on these cones. So yeah, what's actually important about this is that it makes it difficult for backscattering to occur because you've got to change this quantum property of these materials as well. So transitions like this, where you have to scatter, to the opposite sort of momentum, are suppressed. in this sort of result. And so you actually don't get, you get suppression of certain types of scattering in these materials. I thought I'd just give you a bit of an example of how graphene sort of compares to the pure Dirac sort of massless situation. So the Hamiltonian for graphene looks very similar to that of a relativistic Dirac Hamiltonian. The particles here look massless, so the mass parameter is 0. And the particles don't quite travel at the speed of light, but instead they have this sort of relativistic Fermion velocity that they travel at, which is roughly 300 times less than the speed of light. So it's still very fast. Particles and antiparticles instead form this sort of sublattice symmetry in graphene, where you've got like one set that sort of belongs to this A lattice sites and the second set that belongs to this B lattice sites on graphene. The existence of this sublattice degeneracy leads to this additional parameter called the pseudospin in graphene, which describes the chirality of the spinor wave functions. So you might be asking, I guess, sure, you've got all this theory, but like, what can I actually observe? Like, what is this actually going to do to affect observations in my materials and real phenomena that I can measure? So I'm going to illustrate a few of these for you now. So the first one I want to show you is Klein tunneling. It turns out that in quantum mechanics, when you put a barrier of some potential in front of the path of an electron, there's a probability of an exponential decay of actually tunneling through that barrier. When you consider relativistic particles, however, if the barrier height V is much larger than the rest energy, then the dependence on this barrier is actually really weak, and you can effectively have conduction through the barrier. The reason sort of goes something like this. If you have an electron continuum outside the barrier, and the potential of the barrier is strong enough, it'll actually create positron states inside the barrier aligning at the same energies as those of the electrons outside. The matching of the wave functions across the barrier leads to a high probability of tunneling, described by the Klein paradox. And this is a sort of a deep fundamental of the property of these particles. The positive and negative energies are actually described by the different parts of the same spinor wave function. And so they actually, it's very sort of intuitive that, you'd be able to easily sort of tunnel through. And I've sort of displayed the dispersion of graphene up above to show you how those transitions sort of occur. So this was observed in 2009 in graphene using field effects or transistors for graphene FET devices and changing chemical potential locally. And they were able to see a sharp conduction increase when they got to this sort of regime when the potential was high enough. And observed appropriate phase effects. There's another situation called Coulomb blockade or supercritical charge. And so there's a sort of expectation that when the positive charge of a nucleus gets extremely large, that the relativistic quantum mechanics provide a different result to that of regular sort of quantum mechanics. You can think of a semi-classical picture. If I have a really large nucleus, with lots of protons in it, then the radii of my orbiting electrons get smaller and smaller as I increase this nucleus size. Eventually, an electron is expected to be ripped from the sea of electrons around it and leaving behind a positron. And this is sort of there's a supercritical point where that positron will actually become a bound state with electrons around it, sort of analogous to electron-positron pair production, I guess. Normally, you'd expect this to occur on the order of the fine structure constant, which is 1 over 137. So you need a nucleus of size 137, which is really large. But it turns out that in graphene, you can get this at a much smaller amount of effective charge, which is really weird. And this is sort of the reasoning as to why. So in a regular system, you only have this Coulomb potential energy, which is between different charges, and that sort of goes off as one on R, so one on the radius in the separation. And normally in a massive fermion case, you'd have this sort of kinetic energy that's associated with the electrons in the system, and that goes to 1 over R squared. And so it turns out when you put these two things together, there's a minimum energy that results, and you can extract what radius that would be, and so that turns out to be this Bohr radius that you'd expect to observe the electrons at. It turns out in Dirac systems, however, though, that their kinetic energy actually goes as 1 on R. And so you can see that the Coulomb energy actually scales exactly the same as the massless Dirac energy. And so there's a very there's no exact length scale in graphene. There's not this same sort of, point at which I have localized charge in the same way. This allows this sort of supercritical point to occur in graphene with a much lower charge accumulation. So this was observed by adding calcium to graphene and using STM, and you can see here I've got some STM images where they actually measure this sort of localization occurring as a result by introducing these calcium atoms. Another phenomenon that occurs in Dirac systems is this different Berry phase and weak anti-localization. So in general Feynman sort of mindset, I guess, you have different paths that accumulate to some probability of going from A to B. And we sort of knew that there was phase factors that were accumulated during this time, but it wasn't until the 80s that we actually realized that some of these phase factors would actually remain in terms of the result, especially under closed paths. So one generalized quantity here is this Berry's phase, which is really sort of important. In materials, electrons can travel along paths and scatter into multiple objects. This is an example of a backscattering process into the same sort of state or mode, accumulating different sort of phase factors. You can also consider this time reverse version of the same process. The phase factors end up actually producing the exact same result because the signs cancel out. And it turns out that if your phase coherence length is longer than the scattering length, then these phase factors will be preserved. And the backscattering will actually interfere in your system. In regular systems, you'd actually expect this to constructively interfere. And so the amplitude effectively doubles for this backscattering sort of event to take place and leads to a larger resistance with weak localization in your material. In Dirac systems, however, it turns out that these spinors, as you rotate or change the momentum for a backscattering event, the phasing actually ends up being, there's actually destructive interference between these two paths instead, which is a different result. And that actually leads to a lower resistance, resulting in weak anti-localization instead. The dependence on these properties can be observed using a magnetic field. As you increase the magnetic field, you actually destroy the phase information, and so you actually subtract or get rid of these effects from occurring inside your material. One other sort of phenomenon that I don't really have time to maybe explain in detail, but this Berry phase also leads to an additional observation in this phenomenon called the quantum Hall effect. It's basically the quantum Hall effect is observed under strong magnetic fields, and basically you get this dissipationless conduction edge channels that occur in the quantum Hall effect. And normally there's these sort of increments in steps between where these sort of dissipationless channels sort of occur. And I've described those equations on the right there. But in graphene, it turns out that it was measured that you actually get this sort of half level to begin with at 2. And then there's these steps of 4, so 6, 10, 14, so on. And so it turns out you can attribute this factor of 4 to the degeneracy that exists in graphene because of the spin and the sublattices. But there's this half factor that's there, which is different, and that's the result of this Berry's phase as well in Dirac systems. Cool, so let me just touch on exactly what I've been doing with some work in graphene really quickly. I've talked about this before, so I won't go into it in too much detail. But we might, sort of investigate, we know a lot about Dirac systems in general, but what actually happens when we interface that with other phenomena that are around or nearby? So first, if I added a layer near the graphene, I could create a dirty interface and introduce some impurities and these would introduce scattering potentials that actually, scatter the Dirac Fermions in graphene, these quasi-particles. Dielectric materials, an insulator, are often polar. And so their own vibrations can actually generate electric fields through their polarity that might also scatter carriers in graphene. And lastly, the nature of a dielectric material actually means that it actually can sort of screen out impurities that it sees nearby. So these dielectric, polar sort of molecules that form the dielectrics often can, adjust to screen local impurities that are nearby. And so I've been effectively working to analyze the net behavior of all these phenomena for a particular oxide material that we've put onto graphene called gallium oxide. So I'll make a graphene device by I guess doing a heap of lithography in a process like this. And so you end up with some sort of transistor sort of device that you can measure the conduction properties of. By changing the potential of the gate with the silicon underneath it, you can change how many electrons are in your material, which is useful. And this is actually the result of a device from a bird's eye sort of view. And this is the way we actually are able to put this gallium material sort of on top of our device as well to measure its properties. So you can see I've got a bare bit of graphene and then also the gallium covered area too. So I guess, I want to jump into what work I'm actually looking at doing in topological insulators. So topological insulators, I guess, are different to graphene as far as the Dirac system goes, because here the spinner actually describes the real spin. There's not this degeneracy in graphene. The spin's actually distinguished on the surfaces. And that's really important because that's why we actually want to look at these materials. They've got this new sort of degree that we can manipulate and try and modify and interact with sort of magnetically. So topological insulators have these surface states. Here I've got an example of a 3D sort of bulk object in nature, which is the topological insulator. But it's the surfaces themselves that actually exhibit these Dirac Fermions, Dirac properties. You can see that on that surface, that the momentum and the spin direction are intrinsically locked. And that's this property called time reversal symmetry in topological insulators. And what you actually need to generate that is another property called spin-orbit coupling. Spin-orbit coupling, funnily enough, only sort of exists in heavy materials where the fields and the field of the magnetic moment and the spin magnetic moment and the electric field that as it orbits around a nucleus or something like that is actually interacting strongly together. And that really suddenly starts to occur in heavier materials. So here I've got an example of some of these, this coupling that occurs in these materials. And you can see the ones that I've highlighted: selenide, antimony, telluride, and bismuth. And they all are fairly heavy with strong sort of interaction in the spin-orbit coupling sort of regime. The last sort of key ingredient that you actually need for a topological insulator is topology, which is basically a mathematical way of classifying objects based on their geometric properties. So there's an example there of a mug and a torus, which are topologically equivalent. A saucer or a plate, for example, wouldn't be, because they don't have that sort of hole. And you can count these properties when it comes to these sorts of quantities. Similarly, in materials, the band structures can be separated based on their topology. And a Dirac surface is the result of these topological properties in a topological insulator. So we want to mess around with this sort of spin property, which requires some sort of magnetic interaction. By using a magnetic field, we can break the time reversal symmetry of the surface states and make the energies non-degenerate by hopefully opening up a band gap. Unfortunately, you actually need a pretty big band gap, and the Zeeman splitting due to a regular magnetic field would only be millivolts, which is really small, even at like tens of Tesla. And so we actually need something else to be able to sort of achieve really strong coupling and open up a big band gap. It was observed in the mid-1900s that in heavy elements, a pure dipole-dipole interaction wasn't strong enough to produce some of the results that were observed in nuclear systems. And so this led to the discovery of stronger magnetic coupling called exchange coupling, sometimes referred to as RKKY. And if anyone's familiar with condensed matter physics, one of the K's is for Kittel, who you might know a book of. So this coupling can be much bigger than the Zeeman splitting that occurs due to the magnetic field, and that we actually want to achieve in these in these TIs. Sorry. Yeah. Lastly, if we can actually achieve strong coupling, then you might be able to observe this phenomenon called the quantum anomalous Hall effect. Just like the quantum Hall effect, it's a one-dimensional dissipationless edge channel. But the amazing thing here is you actually don't need an active magnetic field to be able to produce this. So if you could actually get this to occur at high temperature, it's effectively a free way of creating a current and conduction between on a material without energy loss, which is really cool. It does require for us to have a chemical potential in the band gap that's opened. The material has to be quite thin to create these 1D channels on the sides. And the time reversal symmetry has to be broken to open this band gap on the top and bottom surfaces. So you normally need to interface it on both sides. So there's some example materials that you can use to try and do this. Firstly, you can dope and make a topological insulator. So add extra atoms that are actually magnetic in nature. And this has been done and actually was able to produce the quantum anomalous Hall effect in 2013. Secondly, we have materials that are topological insulators, but they're also intrinsically magnetic. And so you actually have this coupling by default in the natural crystal itself. And lastly, you can create a heterostructure. So by putting something in proximity to a topological insulator, you hope to achieve the same sort of magnetic interaction. And this last one is where I'm going to be focusing my work in trying to create this sort of phenomena. So what am I going to do that's new? I guess my aim is to actually start using a lot of exfoliated sort of crystals or growing crystals and interface them together in a different way. Normally, in these examples I've shown you in the last slide, lots of these materials have been grown via processes like molecular beam epitaxy, and they're sort of grown one on top of the other. The growths aren't separate or anything like that, and there's the possibility for defects and some of the chemicals to even penetrate through some of the layers, things like that. And so, yeah, I guess something that hasn't been tried that much at all in literature is actually directly contacting two materials grown separately in a sharp interface. And so that's what we sort of want to try and do with these materials that we can actually grow really well. There's also been, since about 2017, a range of new ferromagnetic insulator materials that have arisen. And some of these are actually two-dimensional materials as well, which is really surprising. Yeah, we want to be able to interface these materials with our topological insulators and create that sharp sort of interface. So the way I'll actually go about measuring and checking if we have that sort of interaction that we're looking for, we can observe the anomalous Hall effect to actually check if we've got magnetic interaction between the topological insulator and our ferromagnetic insulator sort of surface on top. And secondly, we can actually observe this coupling as well through the weak localization or anti-localisation sort of measurements and see what that sort of coupling really is. Yeah, so just a big thanks to my research group and everyone that's around to support me, and massive thank you to my supervisors for their guidance. Thanks.
Thanks very much, Matt. Very nice talk. Happy to take a few questions from, I think initially from the audience who are not on the panel. So people who are not staying around later, please do just unmute and sing out a question for Matt.
Or feel free to type it too.
Or bash into the chat. Yeah, great.
I've got one.
Thanks, Berman.
You mentioned positrons a few times. Are these literal positrons or just part of things which behave like positrons?
Yeah, it's things that behave like positrons. So in condensed matter, especially in the band structures and the states that emerge, the absence of an electron in a band behaves. It's like we call it a hole, but it's really a quasi-particle. Like it's a stack of electrons and then there's a gap. And so if I mention something like positrons, I guess what I'm really referring to in these materials is maybe these whole sort of behaviors or things like that. And so in graphene, when you go below that Fermi energy, you're effectively creating holes in your materials. But those objects, have the same. Yeah, I guess I think the main time I mentioned it was probably the Klein tunneling, and the spinor wave functions. It's pretty awesome how that sort of works. So, yeah. Thanks.